Now let's talk about vapor pressures of solutions and introduce something called Raoult's law. Here we're going to deal with a solution that contains a volatile solvent, meaning that the solvent has some vapor pressure. It does evaporate to some extent, but the solute will be non-volatile, meaning that it does not evaporate to a large extent. We'll start by taking a look at a figure that can help us to visualize what happens when you add a non-volatile solute to a pure solvent. So what we have in this figure here is our pure solvent inside of a sealed container. And as I've mentioned before, the solvent is volatile, meaning that it does evaporate to some extent. And there's going to be some vapor pressure that's generated here from our solvent. And that's going to be, you can kind of get an idea for what the vapor pressure is by looking at what's on the meter here, but then also by counting the number of particles that you have here in the gas phase. The addition of a non-volatile solute will cause the vapor pressure of the solvent to decrease. And we can see this in the next image here. So we now add a non-volatile solute, which is represented by the yellow circles here. And by adding that, we realize that the vapor pressure of the solvent has gone down. For one thing, the value on the meter has gone down, but then also you can count the number of gas particles that you have and see that it's decreased, right? It went from 3, 4, 5, 6, 7, 8, 9 down to 6 gas particles here, right? So you're decreasing the number of moles of gas, right? That decreases the vapor pressure of the solvent that you have here. Now, importantly, when we're talking about a non-volatile solute, I'll remind you that means it's a solute that does not evaporate, and it has a very low or even zero vapor pressure at room temperature. And so that's why we don't see any yellow spheres in the vapor phase. It's all going to be in the solution phase. Now, there are a number of examples of non-volatile solutes, and I just listed a couple of them here. It's like table salt or potassium nitrate or sugar. These are all non-volatile. You know, if you left a bowl of sugar sitting on the counter for a few hours or for even days or weeks, the sugar is not going to evaporate. You're going to have the same amount of sugar that you started with, compared to water, which is volatile, right? If you leave a bowl of water out for a few weeks, that is going to evaporate. So here, our solute is something that is not capable of evaporating. Now, why is it that the addition of the non-volatile solute causes the vapor pressure of the solvent to go down? And one way that you can look at it is like this. It helps to take a look at just the surface of the solution, because it's going to be only those particles at the surface that are going to be able to go into the gas phase, right? Particles that are down here have to diffuse their way all the way up to the surface before they're able to go out into the gas phase. So we just want to look at this interface right here. When you have the pure solvent, right, there's completely unimpeded ability for the molecules of the solvent to go into the gas phase. But when you have a non-volatile solute present, some of those solute particles will block the surface of the solution here, right? It's not going to block the entire surface, but it'll block some parts of it, making it more difficult for the solvent particles to come to the surface and escape, right? So what we see here is in this figure, we have, let's say 1, 2, 3, 4 solute particles that are blocking the surface. And as a result, there will be less evaporation because the surface here is blocked. Whereas in the case of the pure solvent, right, we have a solvent molecule here that could escape to the gas phase. But when we look at that same area in the figure that has the solute, it's blocked by a solvent particle that is not evaporating. And this is how the solute can serve to lower the vapor pressure, simply by blocking the surface and making it more difficult for the solvent to find a path to escape to the gas phase. There's an equation that allows us to calculate what the vapor pressure of a solution would be if you have a non-volatile solute added to a volatile solvent. It's this equation called Raoult's law, which says P solution, that is to say the vapor pressure of the whole solution, is going to be equal to only the vapor pressure of the solvent in the solution. The solute contributes nothing because it's non-volatile, right? It has no vapor pressure. Everything is just going to be coming from the solvent. So we're going to have chi of the solvent, that is to say the mole fraction of the solvent. Remember, it's been a while since we found mole fractions. Mole fraction of the solvent will be the number of moles of solvent divided by the total number of moles that you have in the solution. This gets multiplied by P naught for the solvent, And P naught for the solvent is the vapor pressure of pure solvent. So you take the vapor pressure of pure solvent and then multiply it by the mole fraction of the solvent. That tells you what the vapor pressure of the solvent is, which by extension is the vapor pressure of the whole solution, because the solute contributes nothing to vapor pressure when it's non-volatile. We'll take a look at an example that uses Raoult's law. We're told here we have a solution that is made by mixing 50 grams of potassium nitrate, a non-volatile solute, with 150 grams of water. We need to find the vapor pressure of this solution at 25 degrees C, given that the vapor pressure of pure water is 23.8 torr at 25 degrees C. We can begin by writing out Raoult's law, which says that the vapor pressure of this solution is going to be equal to the mole fraction of the water times the vapor pressure of pure water, right? That's our volatile solvent here. Now we know the vapor pressure of pure water, but we need to get the mole fraction of water. So we'll do that in a separate line here. To find the mole fraction of water, we have to know the number of moles of water in the solution, and then divide that by the total number of moles that we have in our solution, right? So that would be the moles of water plus the moles of potassium nitrate. All right, so we'll find some moles here. So for the H2O, we have 150 grams of that, and then we can use the molar mass to convert that to moles. We know that 1 mole of water weighs 18 grams. And so for water, we have 8.3 moles of that present. Then we can also take a look at the potassium nitrate. We know that we have 50 grams of that, and we could divide that by the molar mass of potassium nitrate, which is 101 grams per mole. Therefore, we have 0.495 moles of potassium nitrate. We could put all of that together now to find the mole fraction of water. So the moles of water is 8.3 divided by the total moles of solution. So that's the water, 8.3 moles, plus the potassium nitrate, which is 0.495 moles. Therefore, the mole fraction of water in this solution will be 0.944. 94.4% of the moles in your solution are water. With that in mind, we can now calculate what the vapor pressure of our solution is. What we'll say is that the vapor pressure of the solution is equal to the mole fraction of the water, 0.944, times the vapor pressure of the pure water, 23.8 torr. This solution has a vapor pressure of 22.5 torr. And there we have it. By adding the 50 grams of potassium nitrate, you're able to decrease the vapor pressure of the solution from 23.8 torr down to 22.5 torr, because putting in potassium nitrate blocks the surface of the solution. Not to a large extent, because it's only present in a fairly small amount, right? The mole fraction of potassium nitrate is what, like 0.056, right? So only 5.6% of the surface is going to end up getting blocked, but it's enough to lower the vapor pressure by 5.6% here. That brings us to the end of this video, and up next, we'll talk about colligative properties and introduce freezing point depression and boiling point elevation.